Okay, so we're doing on problems from the kinetic theory of gases. Okay. Okay. What do you guys see here? What's that? I'm sorry? So actually what has happened here is, so this bag of chips was packed at sea level, for instance. So, and then you took it to a high elevation and the air inside is expanded. Why did the air expand?
Because the outside pressure is less.
Yeah, that's right. Okay, so when it was packed, the outside pressure was 1 atmosphere and it was, the air inside was at 1 atmosphere. And now, let's say you come to Denver, the pressure is 80% of the atmosphere, or sea level atmosphere. Okay, and so this is expanded. Okay, so that's the problem. So people buying food in a sealed bag at high, in sealed bags at high elevations often notice that the bags are puffed up because the air inside has expanded. A bag of pretzels was packed at a pressure of 1 atmosphere. So the bag was packed at sea level, and a temperature of 22 degrees Celsius. When opened at a summer picnic in Santa Fe, New Mexico, at a temperature of 32 degrees, the volume of air in the bag is 1.38 times its original volume. What is the pressure of the air? Okay, so we'll use the ideal gas law for this. PV equal to nRT. All right, so you can see that, so PV equal over T equal to nR. So as long as you don't change the number of moles of gas, so this will be constant. Okay. So this combination P1, V1, T1 will equal P2, V2, T2. Okay, so as long as you don't change the number of molecules of gas, the pressure, volume, and temperature in one configuration, this combination will equal that. Okay? This ratio will equal that ratio. All right, they give you, so what they want you to find is what is the pressure of air at the second location. So P2 is V1 over V2 times T2 over T1 times P1. All right, so we'll use mixed units. We'll keep this in atmospheres. P1, the initial pressure was 1 atmosphere, so we'll calculate P2. Of course, P2 will be less than 1 atmosphere. Okay. They give us the temperature ratios. In these formulas, what is the unit? What does the temperature need to be in? What unit does the temperature need to be in? Kelvin. Kelvin. Okay. All right. So P2 is, so V1 over V2 is, they tell you the volume of air in the bag is 1.38 times the original volume. This is 1.38 times that. So this is equal to 1 over 1.38. The temperature is 32 degrees and 22 degrees. 32 in kelvins is 305 degree Kelvin. And 22 is 295 Kelvin. And this is 1 atmosphere. So the pressure at the new location is So I guess Santa Fe is higher than Denver. Denver, the pressure is 0.8 atmospheres. Mm-hmm.
Why did you do 1 divided by V1, 1.38 for the volume? Like, why did you do that?
V2 is 1.38 times V1.
Oh, okay, I see. Got it.
Mm-hmm. All right, so, so P2 is 1.38 times V1. All right, so this problem says a cubic container of volume 2 liters holds 0.5 moles of nitrogen gas at 25 degrees Celsius. What is the net force due to the nitrogen on one wall of the container? Compare the force to the sample's weight. So this is an interesting problem. You guys remember the pressure, atmospheric pressure is 15 psi, so the force on this face is how much? 1,500 pounds. Okay, and so it sort of illustrates that issue. Okay, we'll see that the force that the gas exerts is so much greater than its weight. Okay, so we want to calculate this force. All right, so let's say the side is D. Okay, so the force is pressure times D squared. Okay, and D squared is pressure times the volume to the power 2/3. Volume to the power of 1/3 is D, and D squared. Okay, so that's the force. All right, well, what is this? PV is nRT. So what is the net force on the nitrogen on one wall of the container? Compare them. Okay, so this is a cubic container of nitrogen gas at temperature. Okay, they give us the volume, moles, temperature. So the pressure is nRT over V. Okay, so the force is nRT over V. This is the pressure, and the volume to the power 2/3. So it's nRT volume to the power 1/3. Yep. And now we can put in the quantities. Yeah. So this 0.5 moles of nitrogen. R is a gas constant, 314 joules per moles per Kelvin. The temperature is 25, so 298 Kelvin. Let me move this. And then the volume is 2 liters. A liter is 10 to the minus 3 meter cubed. Yeah, to the power 1/3. All right, so, and all this should work out. Everything is in SI units, so the units for force are newtons. Okay, so that'll work out in newtons. Okay. So 10 to the minus 1/3 to the power 1/3 is 10 to the minus 1. We'll bring that to the top and make that a 5. Okay. So the force is 5 times 8.314 into 298 newtons divided by cube root of 2. all right? So that's 10,000 newtons. So in a, so this is 1 liter, and imagine a cube twice this volume, and the force is that many newtons. So this is about the weight of, most of your weight is about 600 newtons. So that's 1.5 times 10. 15, the weight of 15 people. Okay. All right, now let's compare that to the weight of the sample itself. Okay. So how much, what is the weight of nitrogen? Okay. So you have mg, well, we'll first calculate the mass. The mass is, you have half a mole, and this is nitrogen gas, and the molecular weight of nitrogen is 28 atomic units, and so 28 grams per mole. Okay. So you have 14 grams of nitrogen. Okay. So mg will be 14 grams, which is that many kgs, times 9.8. So the weight of nitrogen gas in there is that many newtons. And what we'll calculate is this divided by that. Yeah, so the absolute pressure minus atmospheric pressure. Why do we define that? I'm sorry? No. So if you go to a store and buy a pressure gauge, that's what it measures. It's easiest to measure. Absolute pressure is a little hard to measure. So all those gauges that you buy at Walmart or wherever, it measures absolute pressure minus atmospheric pressure. So when you measure the pressure in your tires, what you're measuring is gauge pressure. Okay, so gauge pressure is absolute pressure minus atmospheric pressure. So let's calculate the pressure first. Okay, so PV equal to nRT over V. Okay, this formula gives you absolute pressure. Okay, so 3.6 moles. R is 8.314 joules per mole per Kelvin, and the temperature is 298 degree Kelvin, divided by 30 liters. A liter is 10 to the minus 3 meter cube. Yeah. So the absolute pressure, this comes out in pascals. Pascals is Newton per meter square. Okay, this is 1 atmosphere. So the absolute pressure in your tire is 3 atmospheres. So the gauge pressure is absolute pressure minus atmospheric pressure. This is atmospheric pressure. Again, P naught is 10 to the power 5 pascals. Yep. So the gauge pressure will be 1.97 into 10 to the 5 pascals. Okay. So remember, the car pressure in your car tires is how many psi? Yeah, about 34 psi. One atmosphere is 15 psi. Okay, so it's the pressure in your tires is 30. Actual pressure is 45 psi. What will its gauge pressure be if you add 1 liter of gas originally at atmospheric pressure and 25 degrees Celsius? Okay, so when you go fill up your tires, you're adding gas and you're increasing the pressure. So let's say you add 1 liter of gas at atmospheric pressure and 25 degrees Celsius. So what we'll do is we'll find the number of moles of gas you've added. Okay, and when the number of moles added, when the amount of gas increases, everything else being the same, the pressure will increase. Okay. All right, so for part B, N is PV divided by RT. Okay, so you're adding gas at 1 atmospheric pressure. The volume you're adding is 1 liter. .314 joules per mole per Kelvin, and you're adding it at 298 degree Kelvin. So you added this many moles of gas. So this is 100 divided by that. All right, so you added 0.04 moles of gas. Originally, you had 3.64 moles, okay? So the new pressure is 3.64 moles times RT over V, okay? So this expression was that for 3.6 moles, the pressure was that. Now you increased it to 3.64 moles, everything else is the same. Okay, so it's, so the new pressure is, this is what it works out to, 3.64 times divided by 3.6, 2.97 times 10 to the 5. Okay, so it scales up. This is the old pressure. So the pressure increases by 1%, roughly. So this is the new absolute pressure. And to get the gauge pressure, you just subtract 1 from it. So the new gauge pressure will be 2.003. All right, so again, when you go to a gas station and fill your tires, the volume and temperature doesn't change essentially. All you're doing is increasing the number of moles of gas. And so you're increasing the pressure. And that's what you saw. Okay? So let's say if the pressure in your tires the pressure in your tires was 30 psi and you wanted to increase it to 33 psi, you're increasing the pressure by 10%, you would increase the number of moles by 10%, the temperature and volume being the same. Okay? Right, so this problem says some incandescent bulbs are filled with argon gas. Where's argon in the? Yep. So what kind of gas is it? And what does that mean?
It's just one atom.
Yeah, it's monoatomic. Okay. So what is the VRMS for argon atoms near the filament, assuming the temperature is that? Okay. So this is the temperature. VRMS is sort of an average speed of argon, sort of an average speed. It's not exactly, okay. And here's the RMS speed. Okay. 3 kT divided by the molecular mass. So in this formula, K is the Boltzmann's constant and M is the mass of a single argon atom. Okay, now that's a little messy, and this is a small number, this is a very small number. But what we can do is we can convert this formula to that. If you multiply K by Avogadro's number, what you get is the gas constant. K times Avogadro's number is the gas constant. And the molecular mass times Avogadro's number is the molar mass, okay? The mass of 1 mole. Okay, so that's what we'll do. And now we are dealing with big numbers, so that's easier to deal with, okay? All right, the gas constant is 8.314 joules per mole per Kelvin. The temperature is 2,500 degree Kelvin. And the molar mass, what's the molar mass for argon?
Roughly 40, 39.9.
Okay. So, what is it?
39.948.
Yeah, what are the units?
After multiplying it's 50 grams.
So, yep, so 40 grams, that's that many kgs per mole. Okay. All right, so now let's take care of powers of 10. This is 10 to the minus 2. That comes to the top. It becomes 10 to the plus 2. And then we'll borrow 2 from here. So 10 to the 4, square root of that is 10 to the 2. So this is 10 to the 2 meters per second. And the rest is and so the rest is 3 times 8.314 into 25 divided by 4. Okay, so this will work out too. So the RMS speed is 1250 meters per second. Um, does this make sense? Okay, do you guys know what is the average speed of the molecules in this room? You guys remember? It's about 500 meters per second. Okay, and the average molecule is nitrogen, which is 28 units, atomic units heavy. This is 40 atomic units heavy. The temperature is higher, the molecule is heavier, and so that's the speed. Okay. The temperature in this room is what, 300 degree Kelvin. So this temperature is about 10 times greater. Square root of that is about 3. So that's a factor of 3. Okay. And so this is roughly a factor of 3. Yep. Oh, wow. Okay, so this says the partial pressure of carbon dioxide in the lungs is 470 pascals when the total pressure in the lung is 1 atmosphere. What percentage of the air molecules in the lung is carbon dioxide? Okay, so Dalton's law says partial pressure is equal to the fraction of molecules times the total pressure. Okay. So this fraction is what we want to find. Okay. So Ni over N equal to Pi over P. So partial pressure of carbon dioxide is 470 pascals. And what is 1 atmosphere in pascals? 10 to the 5 pascals. Okay, so 470 into 10 to the. Okay, so, and the reason I wrote like that is now if you multiply by 100, you get 0.47% is the fraction of carbon dioxide molecules. Yeah. So for every 100 molecules, 0.47 molecules are carbon dioxide molecules. So for every 200 molecules in your lungs, 1 molecule is carbon dioxide. Okay, so that's what that means. Compare that results to, okay, so this is 0.47%. Okay. And the normal percentage is 0.035%, 33%. So normal percentage in the atmosphere, is 0.033%. Okay, so 0.47% divided by 0.33% is about 15. Okay, so once the air exchange has taken place in your lungs, the concentration of carbon dioxide in your lungs is 14 times that in the outside air. Okay. And that's what that says. Okay, this problem says how much heat must be added to raise the temperature of 1.5 moles of air from 20 degrees of freedom are no longer available. Okay, only the translational degrees of freedom would be available. Okay. And if you took air to the surface of the sun, what would happen then?
And vibrational.
Very good. Then those degrees of freedom would be available as well. Then F would be 7 halves. Okay. All right. So the amount of heat you're adding is, okay. So the amount of heat you're adding is N times 5 halves R times delta T. Okay. And we'll calculate that number in a second. In part B, repeat the problem for the same number of moles of xenon. For xenon, how many degrees of freedom does it have? 3. It's a monoatomic gas. Okay? So you see QV equal to N 3 halves R times delta T. Okay, so it takes more heat to heat up air than xenon by the same temperature. Okay? All right, so let's calculate this number. This is 1.5 moles, 5 halves into 8.314, and the rise in temperature is 8 degrees Celsius or Kelvin. It's the same thing. Okay, so it's that many joules of heat you need. Okay, so you can calculate this, and it'll be correspondingly less. So 2 divided by 2.5 into 1.5. And it should work out to about 149.6 joules. Okay. So again, more degrees of freedom there is, more degrees of freedom there are, the more heat you need to warm something. Okay? Because why is that? Why do you need more? Because when you heat something, you're giving equal amount to every degrees of freedom. So if there are more children to feed, then you need more food. Yeah, yep, yep.
Don't need to change the power.
Rise in temperature in Celsius is the same as rise in temperature in Kelvin. Right. Yeah. Okay. So look at this integral. What does the integral give you? Area under the curve. So if you're looking, if the limits of integration are for a small dv, then this area is equal to the height of this column times the width of this column, and the height of this column is the value of the function at this value. You can take it at any value. So for a small dv, okay, the limit of integration dv, it's the value of the function at this lower limit times the width of that column. Okay. So estimate the fraction of nitrogen molecules at a temperature. So this tells you the number of nitrogen molecules at a temperature of 300 degree Kelvin that have a speed between 290 and 291 meters per second. Okay, so the graph is actually the Maxwell-Boltzmann distribution. Okay. And let's show you the Maxwell-Boltzmann distribution. So here is the Maxwell-Boltzmann distribution. Okay, so this is FV. Okay. That tells you the number of molecules at speed v. Okay. So let me go back here. Okay. So delta n, the number of molecules, will be FV1 times delta V. Okay, FV1 is, it's, so 4 pi n m m over 2 pi k t Okay, so in this formula, that's the mass of one nitrogen molecule, and K is the Boltzmann's constant. And remember, M over K is equal to the molar mass over R. That's easier to calculate. So, and this is the number of what they want you to estimate the fraction of nitrogen molecules. So this is the total number of molecules. I mean, this is the fraction this is the number within that speed. You divide that will give you the fraction. So delta n by n equal to 4 pi m over 2 pi rt to the power 3/2 v square e to the power mv square over 2 rt. Okay. So this gives you, and delta v is 1 meters per second. All right, so I'm going to tell you the numbers. I'm not going to calculate it. It's messy. This is 4 pi. M is, what is M? The molecular mass of nitrogen, which is 28 grams per mole. R is 8.314. V1 is 290 meters per second. Okay, that's 290 meters per second. That's 28 grams. R is that. This is 1 meters per second. Okay, so those are all the values. And do you want me to calculate this? What kind of answer do you think you'll get? What is the average speed of gas molecules in this room? That's the temperature in this room. What is the average speed? 500 meters per second. Okay, so the average speed is somewhere like that. You're calculating this number. Okay, so this fraction will be probably about 1% or so. So this number will come out to be about 0.01. Okay, so that's what it should come out to, something like that. All right. In deep space between galaxies, okay, so this is just about the best vacuum you'll see, and we'll figure out the density of molecules, which are mostly single atoms, can be as low as 10 to the power of 6 atoms per meter cubed. So in deep space, in intergalactic space, the density of atoms is 1,000,000 atoms per meter cubed. Here's a meter cube. in that much volume, there's 1,000,000 atoms. In this room, in that much volume, so 1 mole is 10 to the power of 24 molecules. There's about 500 moles, 1,000 moles. So there's 10 to the 27 molecules. So in this room, there's about 10 to the 27 molecules per meter cube. In deep space, it's 10 to the 6. Okay? So 10 to the power of 21 times fewer. The temperature is 2.7 degree Kelvin. What is the pressure? What volume is occupied by 1 mole of gas? Okay. So if you wanted 1 mole of gas in deep space, what would be the volume that you would need? Okay. In this room, you need just 22 of these guys. Okay. Okay, so I'll calculate the pressure. Okay, actually, we'll do NKT by V. So the pressure is N over V. See, they give you N over V. They give you this. Yeah. So this is 10 to the 6 per meter cube. The Boltzmann's constant is 1.38 times 10 to the minus 23 joules per Kelvin. Okay. And the temperature is 2.7 Kelvin. So this is 10 to the minus 17. Okay, why did I write like that?
Atmospheres?
Yeah, so this is 1 atmosphere. So in intergalactic space, the pressure is 10 to the minus 22 atmospheres. Okay, 1 billion times smaller than the pressure here. Yeah, a little more than that. So if you were in intergalactic space where the density of gas is small, what volume would you need to get 1 mole of gas? 1 mole of gas, meaning if you wanted Avogadro's number of gas molecules, what was the volume you would have to go occupy? Okay, so, all right, they want us to figure it out in kilometer cube. Well, so volume is, so what I'll do is I'll borrow 600 times 10 to the 15 and then take the cube root of that. Okay. So 600 cube root. So 8.43 into 10 to the power 5 meters cube. That's the side of the cube. Okay. And then we'll convert that to kilometer, 843 kilometer cube. So that's the size of the cube. So if you wanted 1 mole of gas in intergalactic space, the size of the cube would be 843 kilometers. 843 kilometers is roughly from here to Atlanta. Okay, that's the size of the cube you would need to have 1 mole of gas in intergalactic space. If you wanted 1 mole of gas in this room, what is the volume you would need? 22.4 liters. That's roughly 6 gallons. Okay. All right, one last problem. The air inside a hot air balloon has a temperature of 370 degree Kelvin and a pressure of 1 atmosphere. 1 atmosphere is 101 kilopascals, the same as the air outside. Using the composition of air as that, find the density of air inside the balloon. Okay. For something to rise in a fluid, what needs to happen? Oh, for something to rise, okay, so let's say here's a piece of wood I put in water. For this piece of wood to rise, what needs to be true?
That has to be less dense
Than the water, okay? So the density of wood needs to be less than the water. So for instance, for hot air balloon to rise in air, the density of hot air needs to be less than the density of the surrounding air. The density of surrounding air, do you guys know what is the density of surrounding air? I mean, what is the density of air in this room? It's about 1.3 kgs per meter cube. Okay, so if you take this much air, it weighs about 1.3 kgs. All right, so now we'll find the density of air in this hot air balloon. So you're looking for an answer that's less than that, because for the hot air balloon to rise, its density should be less than that. Okay? All right, so let's find out. The air inside the hot air balloon has a temperature of that and pressure of this. Okay, so PV equal to N or T N over V equal to P over okay, so this is the molar density, and then we'll convert that to mass density in a little bit. Okay, so this tells you, what does this tell you? How many moles you have per unit volume. Okay, and so this will tell you how many moles you have per meter cube. So N over V equal to, the pressure is 101.3 into 10 to the power of 3 pascals. R is 8.314 joules per mole per Kelvin, and the temperature is 370 degree Kelvin. Okay, so there's 30, in that hot air balloon, there's 32.8 moles per meter cube. Okay, so this much volume of that hot air has 33 moles of gas. Okay, now let's figure out how much does it weigh. Yeah. So mass per unit volume will be, okay, so it's 32 moles. Okay. So let's calculate the fractional moles. the number of nitrogen moles is 78% of that, okay? So 0.78 times 32.8 moles. And what is the weight of nitrogen? 28 grams, that many kgs per mole. So the moles will cancel, you'll get kg per meter cube. Okay? So that's the contribution from nitrogen. Yeah. So you'll get, this will be the density. Okay? So the density of hot air. Then what do we have to do? Then add the contribution from nitrogen, from oxygen, 21% moles per meter cube. That's how many moles of nitrogen you have per meter cube in the hot air. And what is the molecular mass weight of nitrogen? 32 into 10 to the minus 3 kgs per mole. And then 1% argon. What is argon? 40. Okay, so the 32 is common. I'll pull that out. .78 into 28 plus 0.21 into 32 plus 0.01 into 40 times. All right. So the density of hot air is 0.95 kg per meter cube. Okay? And this is less than the density of cold air, and that'll rise. Okay? So what you're trying to do is when you heat the air, you're trying to expel the gas molecules. Okay, you're raising the temperature, you're expelling the gas molecules, decreasing the density. So you decrease the density so that it can rise. Okay, you got to decrease the density enough to be able to lift the basket and all that kind of stuff. Okay. All right, guys, so that